Okay, so now we'll continue on. So after we've gone over this distance maps topic, um, kind of the next area we wanted to cover is this idea of topology and skeletonization. And so if we're looking at particular structure types, and for this example, we use cellular materials for material science. Trabecular bone also falls under this category, and that's basically where you have a material that's made up of unit cells. So it has nothing to do with like cells in the sense of biology. It has cells in the sense of sort of unit cells that it's built up of. How can you analyze this material well? And so again, we see that with a structure like this, if we were to do connected component labeling and sort of basic shape analysis, this wouldn't give us any useful information. A distance map might be slightly more useful, but again, we've seen this histogram from a distance map in the last slide. This here doesn't necessarily make it that easy to understand what's going on in the structure and doesn't give us any of the parameters that we're interested in. And so what we're kind of interested in knowing is which structures are connected, how are they connected, how can we express this network in sort of a simple manner, and how can we start to analyze things like tortuosity and branching. And so when we see this structure, we can see clearly that there's sort of a unit here, a unit here, a unit here, a unit here, and they're connected with sort of these little channels. But how can we represent that in an easier way? Because of course the computer doesn't see that, the computer just sees a list of voxels. And so the first step we do is taking this distance transformation. So we calculate the distance at every point. In this one, we just use the standard Euclidean one, and we see that this gives us sort of a nicer visual of the object that we're trying to look at. And if we were trying to separate these components, we now see that we could simply perform a threshold to cut these pieces apart. Does anyone see an issue with using just a threshold to cut these components apart? Nope.
What are you seeing as the components?
Oh, these little blocks.
The white,
the way up
the
here.
blocks.
Yeah, sorry, the components are the blocks. The white is sort of the background. Yeah, so this is the original image. And these are the pieces that are made up. So if the pieces were the white, we don't need a more complicated analysis because they're already very nicely separated. Since the components are these boxes here, they're all one giant mess. How can we separate them?
On the question about the threshold, if they're connected by very high value, I can see an easy cutoff threshold.
Right.
Unless you were to somehow look at distance to another distance on that, and then squeeze out the thin connections, so them squeeze down value, and then do a threshold.
Yeah. So the problem we have with this, just as you mentioned, is that the distances are different in different directions. So that we see at this point it's very thin. So this would be kind of easy to cut. If you take all the really low values, you can just cut there. But these points, for example, are very thick. Trying to get a threshold that would allow us to divide those two components apart would get rid of almost everything in the image. And so when you sort of have this inhomogeneity or large variation in how tightly or well connected the components are, then simply doing a threshold analysis isn't going to help you with that. And so that's where we need more advanced tools to kind of help us break apart this structure so that we can describe it well. And so what we do here is we do something called skeletonization. And so what's nice about this is that we can actually use some of the tools that we've already learned to perform this analysis. And so one of the things we can do here, which is similar to the idea of sort of a second distance map, but actually even easier from the implementation, is as engineers who've taken math classes before, these appear as sort of local maxima. And so all we have to do to find these points is find where the derivative is 0. And so if we think about this distance map as sort of a 3D surface, instead of just being a distance map, we can then imagine sort of the points that are the peaks or the sort of ridges that we're interested in this image are the points that are on the top of the surface where sort of the derivative is flat. And so what that allows us to do is we can calculate the Laplacian, which is an approximation for this derivative kernel, on the image. So this is really just a filter, exactly like we've had before in sort of the image enhancement section. And so it almost seems like we're going backwards, that we go to having this nice segmented image. We then turn it back to a grayscale image and then apply filters to it again. And so it starts to get kind of a bit redundant, or seemingly redundant in the way we do this analysis. But in fact, this is the easiest way to process it. And we get sort of a very nice skeleton out of the image. And so when you look at this image, you see that sort of these Laplacian gradient points match up well with what we'd sort of expect as those ridge points that we're looking at. Sorry, these are the second derivative, not the first derivative, but it gives us the same result. And so we calculate these values on all of the points in the image. And then what we can do is we can create a skeleton by thresholding this image, by combining this sort of slope or Laplacian information with the distance information. And so what it allows us to do is we can sort of take this data set and look at it as sort of a feature vector, and we apply two different criteria to it. And so what it lets us do is we can sort of come up with a skeleton by finding the overlap between the points which are not on the surface and the points which sort of have a low or a high Laplacian value. And so by matching these values up well, so if you have sort of a minimum slope or Laplacian value of 1 and a minimum distance of 2, you get these areas. If you then have a minimum slope value of 0 and a minimum distance of 1, then you get these values. And so based on how you tune these parameters, you'll change substantially the outputs you get in this system. And so by changing the thresholds you have, you can choose how sensitive you are and what details of the structure you want to extract or not. So you still sort of have quite a bit of decision making to do, because if you see for these values, it includes lots of points here that we might not consider relevant as sort of describing the topology of the structure. So if the structure we're interested in is just these points here, and that the actual kind of shape or that these boundary regions aren't of interest to us, then this would clearly be too low of a threshold to extract just those points. And so it's about kind of balancing these parameters well. And we see here that this threshold is probably too high because we don't maintain the connectivity that we want to have. And so we see many of the structures, but some of them sort of disappear or aren't fully connected. And if you're doing, again, sort of a flow simulation or some sort of further analysis on this data, having this structure not connected will drastically affect the results that you're getting at the end. And so you'll want to make sure that these parameters are tuned so that they match your expectations for the system and what you plan on doing with the data later. And so here we sort of find a slightly better sort of combination of parameters that gets us most of the skeleton of the network without having too many artifacts. And then what we can do is sort of how do we improve this structure further? And sort of the options we have here are to sort of adjust the threshold values and try to play with that, or change the image and smooth the image out, or perform morphological operations on the image before. Or we can try to prune the structure based on our understanding of what it should look like. And so typically the pruning strategy tends to be better because it's less kind of resolution dependent. With these stricter thresholds or playing with the image before, if your resolution's higher or lower, all of those analyses change. And with the pruning, you can start to put in parameters that are independent of how big your structure is and what resolution you're measuring at, because it's based on some sort of model or understanding of the system. And so with this example, it's looking at the cellular material, and you know that maybe these branches that come off here are not relevant because they're too short or they're too thin to really represent a meaningful structure in your image. And so then you can automatically remove those sort of with this criteria. Then, what we want to eventually get with a skeleton is a 1 pixel thick or 1 voxel thick structure that sort of connects all the different points in the image. And so here we sort of have a structure that is most of the time 1 pixel thick. It's not exactly that. And so we want to prune it to get it even closer to that value. And now what we want to look at in this structure, and this is really kind of the topology metrics we're trying to extract, are sort of junctions, segments, and terminals. And so when you have a network, when you have a topology that you're looking at, you can classify each point in this topology or in this graph as being a junction. And that's where it's connecting sort of 2 or more different points. Well, actually, we can start at the very end. A terminal is sort of where it's at the end. A segment is sort of where it's connecting 2 points together. And a junction is where it's connecting more than 2 points together. And so what's, again, nice with this is that we can use this idea of neighborhood that we've had before, where we did that with morphology, with this component labeling, with these other sort of approaches. And we can look at each point and count the number of neighbors it has. And so rather than looking at the neighbors for doing connected component analysis, we look at the neighbors to try to assess what kind of point this is. And so here we can classify each of these points into a junction, and that's where there's sort of more than 2 points in its immediate neighborhood. A segment, and that's where there's only 2 points in its immediate neighborhood, and so that's where it's 1 above, 1 below, 1 to the right, 1 to the left. It doesn't necessarily mean it's straight. It just means that there's only 2 points that it sees in sort of its box around it. And terminal, and that's where it only sees 1 point. And so if you're looking at this structure and you're trying to figure out, how the flow goes through it, then knowing where the terminals are would give you a point where you could have the flow start and have the flow end. And then you could see how well they were connected or how well the flow moved through that entire structure. And so this neighborhood is quite important to define well. And so if you define it with sort of a 4 neighbors, a 6 neighbors, a 4 neighbors, 8 neighbors, or 4 neighbors or 8 neighbors in 2D, or 6 neighbors or 26 neighbors in 3D, whatever that definition was, you have very different values for what junctions, segments, and terminals are. And so again, this neighborhood definition needs to be adapted to the images that you're looking at so that you get a meaningful value out of your system at the end. And so if diagonal connectivity is connected, then that's sort of something you want to keep. Then you would use that, and so this would be then sort of the box neighborhood for a slightly thicker structure and what that looks like. And if this diagonal connectivity is not realistic, then you take that out, and then you get a different classification for the same structure. And you see here that if your structure isn't 1 voxel thick, you see in both of these images, that because these structures are not perfectly thin, that we get values out for junction segments and terminals that aren't really meaningful. So we see that all of these points in here are classified as junctions. And they're definitely not junctions. They're definitely part of a segment that's just going in a straight line. And so that means we haven't thinned our structure enough, and this classification isn't meaningful. What we want to see is sort of points like this, where this line is identified as a segment. This is a segment as well. There's a junction here, and there's a segment here, and there's a segment there. And both of those segments then end with terminals. So that part matches well. The other parts have problems that make it difficult to use. So we then can go through these structures that we've assembled. And so basically they're just lists of voxels that have now been labeled into junction, segment, and terminal. And we can count the number of junctions that we have, the number of segments, the number of terminals, And this gives us a nice descriptor of the structures that we're looking at. And so when you're looking at these kind of parameters and you want to assess how is the structure evolving, how is the structure changing, then this gives you a very nice way to assess that. You can also then look at sort of what's the average length of each segment that we have, what are the number of incoming segments, so how does the topology of that network change? And where this is particularly interesting, which is what Giannis spends most of his PhD working on, is analyzing these structures for sort of baby rat lung images. And so this is where you're trying to evaluate how the lung develops. And so here you sort of have a alveoli, or you sort of have the trachea, and then you have sort of breakdown into alveoli and these other smaller structures. And understanding where there are segments, where there are junctions, how much branching is going on, and how does the lung actually develop is quite important, because when this doesn't happen correctly, it can cause a number of very serious diseases. And so being able to quantify this and understand that structure well brings a lot of additional information to this sort of analysis. Boom. Furthermore, once we've sort of established the skeleton, we can start to evaluate other interesting parameters. And so one of them that's very commonly used is tortuosity. And basically it's the ratio between the arc length of a segment and the distance between the starting and ending points. And so this kind of L over C metric. And what a high degree of tortuosity indicates is that sort of the flow or the network is very convoluted. And if something's trying to flow through it, it's not going directly where it needs to go. And so if you're looking at a geological process, this would be sort of, diffusion and fluid transport. One of the areas that we've worked on before with this is when you have sort of nuclear waste that you're trying to deposit, how fast it diffuses into things like groundwater is quite important to understand. And so if you're dealing with materials that have a very low tortuosity, then this can happen in years instead of thousands of years. And so being able to assess this on a very, very small scale is very important for being able to deposit this material well and knowing what's going to happen to this material, because you know how slowly it stops being radioactive. And you need to know how fast it diffuses, because if it diffuses faster than it stops being radioactive, then you have a major problem. Sort of in chemistry, this sort of analysis allows you to perform sort of a size exclusion chromatography. So when you're trying to separate different objects, knowing how well this or how high this tortuosity factor is in your system will help you sort of distinguish the different components you're looking at. And sort of in vascular tissue, this can be a pretty serious sign of pathology, because you'd expect sort of two points or two regions to be connected with a very, very short, direct vessel. And if it's very convoluted or it's not formed well, then this can be a major problem. So being able to evaluate that for that system is quite important. Cool. So now we kind of switch gears again. Are there any questions on the skeletonization part? Okay. So we have some exercises that go over that if you're interested in finding out more. Of course, that was just a very cursory introduction. To do skeletonization on really large images is a very, very challenging problem, and there's lots of important steps that come in. We briefly just mentioned pruning, and there are hundreds, if not thousands, of different algorithms which perform pruning using different criteria. And so knowing which one to use and which one works best under what circumstances is really kind of an art. And so it's worth spending time learning about those methods in more detail if that's something you really have to do. For people who don't have to do that analysis, it's then too much detail, but this just kind of shows you what steps are involved in the typical analysis of that structure. So the thickness map is sort of building off of what we had from the distance map, because the distance map didn't really give us the information we were interested in. So the distance map is a major improvement over sort of the segmented black and white image, but it's not quite as useful as what we'd really like to have. And so the thickness map basically says that for an object, what we want to calculate is for every point inside of this object, what's the largest sphere that contains that point and is entirely contained within the object? And so here we have this sort of elongated cell object here. And, a sample point, it may be there. Resolution's not very good, but let's say here. And sort of this sphere forms the largest sphere that contains that point and is entirely contained within the object. And so basically what it says is it says at this point, this is the thickness of that object. And what's nice is that anywhere kind of inside this sphere, you'd expect that value to be the same. And so it doesn't matter if you're right on the surface or if you're completely in the middle, you have the same thickness value. And with the distance map, if you're right on the surface, your value is 1, and if you're in the middle, your value is 20, or whatever the size of your object is. And with this one, it's then constant. And so now you know for each point in your image, or if you could create this, you would know this for each point in your image, what the thickness or what the size dimensions of that point were. So if this were, if you're looking at diffusion in sort of a process like this, this is kind of the area it would freely move around in before it would encounter other objects. It's really useful for spherical objects. Of course, for spherical objects, you don't necessarily need to do this analysis. It's already given to you because you know all your objects are spherical. But for cylindrical objects, so when you look at things like vessels or pipes or sort of other connectors like that, and you want to know how thick the object is, this gives you a very accurate representation of that. Whereas if you were to just look at the area or the volume or the orientation, that wouldn't really tell you anything about the thickness. Even the distance map wouldn't tell you the thickness because if the thickness were constant, the distance map would be helpful. But as soon as there's any variation in that, then you can't really use that distance map anymore. And what's nice is now you have this tool which basically says anywhere inside this pipe, you have the radius of that pipe. And so if the radius gets larger or smaller, or there are sort of constrictions, then you can just look at that map and look at what the values are and see where those constrictions come in. And so now if we take kind of the single cell image we had, and we perform the thickness map on it, we have the distance map here, and then we go through this distance map and sort of fill up the objects with spheres or circles, in this case, of the largest radius that fit inside them. And so what's helpful here is that we now see that sort of this point has a very low thickness because there's not a very large, the largest circle that fits inside there has a radius 1. And these ones have much larger radii. And so the ones that are sort of more circular or spherical tend to have then larger homogeneous values for this. Because this is elongated, we see that kind of towards the boundaries it gets smaller in sort of the maximum radius that it has, but it's still higher than this bottleneck. We can then do kind of the same thing for the background image, that rather than looking at sort of the distance map by itself, we look at this thickness map, and we can see here sort of this all turns into kind of one homogeneous piece, because this all has the exact same distance from the background. And then we see these sort of boundary points where there are sort of rougher regions in the surface that don't fit well into this sphere model. Boom. We can also calculate, so if we think about the computation of this, just like with the distance map, that the raw computation power of going through each point in an image and figuring out what the largest sphere is that fits inside this point is a very complicated problem, because it's not just measuring the distance or anything like that. It's about looking at all the possible spheres that contain this point and checking to see if that sphere fits inside the object that you have. And so, this has then a whole range of different possible centers that you have and a whole range of different possible radii that you have. And so if you were to go through it computationally, it would sort of be on the order of n cubed to calculate all of those possible spheres, and that would be very inefficient, and particularly for 3D imaging, almost useless because it would take months to calculate for your image. And so what we can see here is that the skeleton that we've calculated before allows us to there's a connection between that and the thickness. And so once we found these kind of local maxima, these are good guiding points for where these spheres are located that we want to grow out. So rather than looking at each point in the image and trying to figure out how many possible spheres fit inside there, we start off by focusing on the skeleton, or sort of these local maximum points. And then we grow out all of those local maximum points to get the thickness values. Yeah, and so this gives us a much quicker way of getting to sort of the skeleton to all the points that we have. And so if we calculate the thickness from the skeleton, we get sort of this map here in 3 seconds. Of course, this is a very small image, so for much larger images, these times get much higher. And if we do a full thickness map, it then takes 10 seconds. And so it's at least 3 times faster. And then in 3D images, the factor's even higher. And so we get sort of an approximation for what the structure looks like. And it's nice because we can now see the different, from the thickness map, it's much easier to see the different sizes of the objects. And it's easier to get an assessment for how large sort of this average unit is that we have. And, if we do the statistical analysis, of course, if we use a more detailed skeleton, and so here we took sort of higher thresholds that have sort of fewer points inside them, you can take lower thresholds, and your skeleton starts to match your final skeleton much better. But what we see is that for most of the analysis that we do, this actually isn't so important. And actually, what we want to have isn't necessarily the thickness at every point, because we see in this image, for example, there's a lot of yellow points here, and at the borders, which may or may not be interesting for us. And so a lot of times you want to actually exclude many of these small regions because that's not what you're really interested in seeing. If you focus at every tiny pixel that you have, you'll have a lot of pixels that sort of have 1 or 2 on the thickness value that may not be meaningful for the analysis that you're trying to do. So here, if you're trying to focus on the objects and see what the average size of those objects are, then including the distances from these really thin regions will just sort of skew that value. And so choosing this distance map or the skeleton to match well, in many cases actually gives you a more meaningful result than taking the full distance map. And so what we see here is that it actually matches perfectly for all the larger radius spheres, and for the smaller ones it just sort of cuts off. So it doesn't have the smallest radii that we have because we applied that threshold first. If you get rid of that threshold, then it matches perfectly. But it takes longer. And so here you can then increase these values, and you get it down to half the time it was before, and you can now you match the top values very well, but the lower values you match less and less well. And so it's sort of here important to decide which structures you're actually interested in looking at and how much time you want to take to do this computation. And what you'll see is that for a lot of the images that you have in 3D, calculating this distance map, to give an example from a project I worked on with bone, where if you have an image that's 2000 by 2000 by 2000, calculating the distance map for that, I think took 12 hours. And so a factor of 3 or more, so I think in this case almost 10, makes a huge difference. And so if you're not really interested in those tiny objects, then knowing how you can cut it down well to focus on the things that you're interested in is very, very important. Because if you have to wait 12 hours for your analysis to run, and you have thousands of samples to do, and you're trying to adjust the parameters, then it's a huge waste of time. And here, where it takes 1.7 seconds versus 10 seconds, that doesn't really change anything for you. It's still more or less interactive. So here is what this kind of looks like in 3D images. And one of the really great benefits of doing this kind of analysis in 3D is that you can take a really ugly data set and sort of like I mentioned before, that you have sort of this insensitivity to small changes, which is what the distance map gives us. And because this is built on top of the distance map, it sort of preserves this property very well. And that we can put an image in like this. So I think this is, again, a beer foam structure. So it falls into kind of this cellular material where you have the bubbles, and you have then the beer in between the bubbles. And you want to understand sort of how large the bubbles are, how they're connected together, how the radius of these bubbles is sort of changing with time. And if you look at this image, which is the kind of image you get when you do really high-speed tomography, because you don't have enough time to really make a high-resolution, low-noise image, because the bubbles themselves are changing so quickly. And so if you took more time to take the image, you would have less noise, but you'd have more blurring artifacts. And so it wouldn't actually make the quality of the image better, it would make it worse. And so here you have lots of noise, and then you see that there's lots of sort of holes in your image that you would ideally not have. But when we perform sort of the thickness analysis, where we say sort of the background is air, we can then calculate the size of all of these bubbles. And of course, we get some artifacts where these small holes were, but the central structure is preserved very well. And so we're able to see where the large bubbles are, and we can simply make a cutoff of bubbles that are smaller than this size are probably noise or not interesting to us, and then we can focus on that kind of analysis further. And this is very helpful because if we were to try to do another kind of analysis for this image, even component labeling, we would just get a mess because the data is so noisy, and it would be very sensitive to how many of these holes or tiny holes you had in the structure, because for connected components, all you need is one pixel touching, and your analysis changes completely. With thickness, it's then much more sensitive, or much less sensitive to these tiny variations. So now, to kind of switch over to kind of the last major method that we'll build off of this distance map is Watershed. And so this was the idea we had before, where we're looking at the cells, I think were here. You're looking at these cells, and you want to be able to say that this is 3 distinct components. And so the thickness map were able to give us the thickness kind of each one of these components. We could see that there was sort of a smaller sort of bottleneck between these components here, but it still doesn't tell us that this is 1, this is 2, this is 3. It simply gives us a thickness map. And so what we want to be able to do is now separate this structure into different components. And does anyone have a suggestion of how we could do that? Well, has anyone heard of Watershed before?
Brain perfusion. Obviously, it comes from physiological structure where you have water, combining water from different sources.
Yeah. So how might that be relevant for a distance map?
So we want to find the points where you have an overlap of influence from the different central points.
Yeah.
So points that are the same distance from
Kind of.
the threshold on a specific position on a range of distances, and you maybe get the central points of connecting points. So you
So think more from the watershed perspective. What is a watershed? So what did we actually imagine this distance map of as before?
let's say if this was the watershed, might be you have 4 fountains and the water coming together everywhere else, and the 4 fountains would be where the brightest points are in this case.
Yeah.
So if you want to have 4 different objects, you could threshold define a range which represents the peak, and say that those are the sources of water.
Yeah.
So that would you?
Yeah, so that's one of the ways you can calculate that. The way we have here, or sort of the typical visual, I think that works well for this, is that you imagine this as, You don't have to do a local balancing. What you do here is you just imagine, I mean, the implementation, of course, different. What you imagine here is that this is a height profile. And that rather than this being a peak, this is then a valley. And so the watersheds, so this is now basically a topological map that you see, that, this is sort of a valley, this is sort of a gap between two valleys, and this is what the structure looks like. And watershed is, of course, where does the rain collect? And so what you want to do is then rain on this image and see where the water collects. And so that's actually quite easy. The watershed is just flowing downhill. It doesn't require any sort of further specification than that. You can give it more, but you don't need to. And here you sort of say the water is initially distributed evenly in all of the points. And here we show the water as being kind of this red on top. And what we say is that the water flows downhill. And so there's some sort of gradient that we have, and we want the water to just follow this gradient. And so at each point, you say you have the water look at all of its neighbors, and it finds its neighbors with the highest or lowest value. So in this case, because it's distance from the surface, we look for the highest value, but it's actually going downhill. And if it finds a value there, then it goes in that direction. And so what we see is that after one step, we have zero water at all of the boundaries, and the water is starting to collect into sort of these basins. So that in this middle point here, we already have 9 pixels, or 9 sort of buckets of water that have collected there, and at the points around it, we have more. And so we can then perform more iterations and see that after 2 steps, we now have a huge number of sort of empty buckets here. So all of these boundary regions are completely empty, and these points in the middle are getting higher and higher. And after 6 steps, we now just have points in the middle of these 4 different objects. And so it basically just followed the gradient down to the center of those objects. And so that's how the watershed transform works, is that you see where this water flows. This is, of course, the least efficient implementation you could make of the watershed, but conceptually I think it's the easiest to understand because it doesn't require thinking about all the details. It's just looking at this and thinking about where does the water flow through this image. Then what you do is you simply regrow the points to the original water that they came from, and now we've divided this image into these 4 different regions, and we know that all of them are separate. And so we know that we're done because if we try to flow downhill here, nothing changes. And so that's a very common sort of finishing criteria for these iterative techniques, is that once the values stop changing, or once there's no longer things that are moving, then it's complete. And what's nice about this is that there's no possible state where it sort of fluctuates back and forth, because water only flows downhill. And so you are forced essentially to get to this final state, and once things stop moving, you know that you're completely done and there's nothing that can happen. Other techniques aren't quite as clear with their sort of finishing criteria, but watershed is. So now we've regrown it back to these 4 different regions, and now we've divided this object, which was connected together, into these separate components. And we can see that for more complicated objects, sort of like these points that we showed before, we have this distance map here, and then we get the watershed, which breaks them apart quite well. We then get interesting artifacts. That sort of, if you have connection regions between these points that are too long, it starts to think that that's a new object. And so watershed isn't sort of a magic bullet. For most real structures, you'll be required to tweak it a little bit, because simply following the gradient down will give you structures like that, which maybe you wouldn't expect to see in your image. And in some cases, you'll lose structures entirely. And so in the implementation of the watershed technique in Python, the top structures, because they're connected to the top of the surface, disappear entirely. And so if you're interested in those components, it's important to know that that sort of thing can happen, because that would drastically affect the results that you get out of your system. Kind of the last thing we'll talk about briefly is curvature. And so curvature is, again, one of these very important metrics because it's looking at surfaces or interfaces, and it's very important for diffusion, coarsening, and lots of other sort of changes that happen inside complex structures. And it's very closely related to material science and chemistry. And so being able to assess the curvature of a structure is very important. And basically what the curvature represents is that if you sort of have a curve, the curvature of the curve is the sort of rate, the circle that would fit inside that small region of the curve. And so the curvature at that point is then 1 over that radius. And so in 1D or 2D, it's much simpler to define because there's only sort of one circle that you could take along this curve and fit to it. And what's important to note with this is that if you have a very high radius, your curvature is very low. And if you have a very small radius, your curvature is very high. And so the curvatures and the size of the radius are a little bit, or for the first time, can be a bit counterintuitive. But once you think about it in more detail, it makes more sense. One of the ways you do this, or the way you typically do this in 3D images, is you look at the surface normal. And so here, when you have a 1D curve, the normal is sort of this vector out here. And then you can define the circle based on this vector. In 3D, this gets more complicated. And so you have to then look at all the surface points you have in your image, and you calculate the vector on top of this. And so what this means for us is that we can't calculate the curvature just on the 2D values or the pixel values that we have. We have to calculate the curvature on the surfaces or the perimeters that we generate for our objects. And so all the curvature analysis that we do is dependent on how well the perimeter or the surface area is being calculated. And so that's one of the things that makes curvature kind of difficult to use, is that if you can't calculate the surfaces well, then the curvature you get out is meaningless. And so it's sort of fully connected to how you calculate that stuff. And so here what you do is you calculate all of these surface normals at every point in your image, and then you're able to see sort of what sphere object or what radius sphere object matches your surface at that point. For 3D, it's then just not a simple circle. It sort of has different sizes and different dimensions. And so when you look at sort of the surface normal that you have at each point, you can define the curvature at each point in this image in a huge number of different ways, which is why typically what you do is you you can define an angle at which the sort of plane that you have, which contains the point that you're interested in, and the normal can be freely rotated. And so basically you're taking slices of the surface of your object that pass through the point and the normal to the surface at that point. And so as you rotate this angle, you're looking at different values of this sort of cross-section. You can then define the two principal curvatures for the surface that you have by taking the maximum and the minimum for the curvatures that you calculate at each of these angles. And so, to kind of take a concrete example, if you have a sphere and you look at the points on the sphere, I don't have a better image for that, unfortunately. If you have a sphere and you have a point, the surface normal is very easy to calculate for the sphere. It just simply goes out at this direction. And you have a plane that cuts through it. But you have an infinite number of planes because you can change the angle of that freely. And so when you have a sphere or a sort of a round object, at this point, you have sort of a curvature this way. So it's sort of a negative curvature or positive depending on which side of the surface you're on, that goes down like this. As you rotate the plane, it stays more or less the same, and if it's a perfect sphere, then it's the same independent of what angle you look at. If you have a more complicated object, so if you imagine kind of a saddle, for riding a horse, you can take this saddle, and at this cut through it, the curve is sort of this, so it's kind of negative going away from your point. And at this direction, it's then going upwards. And so you can actually have completely different curvatures depending on what angle you're looking at. And that's why these two principal curvatures are quite important to define. And so you have the maximum and the minimum. These can actually have different signs. And if you're at a point like a saddle, then it will have a different sign. And then you have parameters you can calculate from this, like mean curvature, which are the average between these 2 points. And so in the case of the saddle, the mean curvature could be 0 or close to 0 because you have one positive, one negative. And the Gaussian curvature is then the product of this. And so if you're looking at spheres, you'd expect them to kind of agree in sign. And saddles, you'd expect them to disagree in sign. And for planes, you'd then expect it to be 0. And so this kind of tells you if the point you're looking at is a sphere, if the point you're looking at is a saddle, or if it's a plane. And so this kind of helps you visualize or understand your data sets a little bit better. You can then calculate this quite easily for 3D samples, and so you can take a complex structure and you can calculate what the mean and Gaussian curvature is at each point inside of your image. What you see from this is that you have a lot of boundary effects, and so at most of the points in your image, this is fairly close to 0. And you have lots of extreme values at the edges, where the curvature is then sort of infinitely high, because you just have this very, very thin wall at the top, or some of these sort of junction points down here. And so where kind of the curvature can be very helpful is if you're looking at sort of a bunch of spherical particles or that are melting together, and you want to go from, and you want to measure how your system's progressing from the spherical particles to this sort of annealed mesh of balls, then looking at the curvature would give you a very sensitive metric to see exactly how this change is proceeding. Because spherical objects all have this sort of positive sort of Gaussian curvature and a mean and positive mean curvature. And as you get closer and closer to this mesh of balls, you'll have many more saddle points. And particularly when you go from objects that are not connected to objects that are touching, you'll develop a huge number of saddle points. And so as we saw before with this distance map, where we had the distance map not change at all, when we went from disconnected objects to connected objects, the curvature changes massively. And so if we're dealing with very noisy systems, we want really insensitive metrics. But if we're really trying to see, are these objects connected or not, then we want really, really sensitive metrics. And so that's where curvature can be very helpful, because then this has a completely different curvature than these two circles separately. And so depending first on the quality of your data and second on what kind of analysis you're doing, this curvature can be very helpful for describing what's going on in your system. Of course, the moment you have a single point here that doesn't fit in well with the system, you're going to have a curvature deviation that's then, as we see in this image, shown as, these bright red points at the edges. But if you can control your noise and filter out regions that are useful, then you can get some reliable information on this curvature fairly well. One of the other things you can do with curvature, which is similar to what we talked about with anisotropy, is you can get this characteristic shape out of it. And so basically what that means is that you can scale the curvature values you get, or the distribution of curvature values you get, by the structure size, or the size of the image and the resolution that you're looking at. And then you can get a kind of characteristic shape, where you can see how does the distribution of curvatures change as your object evolves. And that means even if your object is getting larger or getting smaller, you can show that this characteristic shape is preserved or isn't preserved, which can be very helpful for seeing how a system is evolving with time. Because, for example, if you had these spheres and you'd expect them to all grow equally, then the characteristic shape would be completely constant. But if some of the spheres are starting to deform, then that's where this characteristic shape would start to get away from the values that you're looking at before. So kind of with the curvature, the take-home message is that kind of for folds and saddles, they can help you characterize those kind of points, which are typically difficult to look at with ellipsoids or thickness maps. The thickness maps don't really tell us anything about where these points are. And they can provide very good scale-free metrics for assessing structure. It's also helpful, depending on the image and the scales, to look at these images and see if there's useful information you can get out of it or not. So we see with this one that the Gaussian curvature isn't very helpful, but the mean curvature has some information that might be relevant for doing further analysis. And so that's always kind of the important check to take. The reality of curvature is that for most imaging data sets, it can be it's a very noisy and difficult parameter to work with. And so if you don't need to use it or there's other techniques, that can be a much more robust way of assessing what you're looking at in your system. Where it works best is, of course, in simulation environments. And so if you're making all of your data and you're not measuring any of it, then curvature is a fantastic tool. But if you're measuring real noisy data, curvature can be very difficult because it is so sensitive to small changes. There are, of course, a huge number of other techniques. We just talked about a very small category of them. And so if you're interested in looking more or learning more about these, one of the, most of them are actually made as plugins for Fiji or Nime or SciPy or Scikit Image if you're using Python. And they can provide a huge number of additional components that you can extract from images. And so things like directional analysis. So if you're trying to see how well aligned different components are in your image, you can use this, which sort of uses a Fourier transform of the values that you have. There's tubeness and surfaceness, which can be used to kind of characterize binary images like curvature, but it operates a little bit differently. And it's a bit more robust to noise and other small variations. And so that can be helpful. Fractal dimensionality is a tool that physicists tend to use a lot. How well it's actually usable for most scientific experiments, I can't really say. But basically you see sort of how does the structure you're looking at or the value you look at change with scale. And so there's an interesting paper here where they show kind of how the structure of metallic glasses scales as you move sort of up and down the dimensions. And that then gives you an ability to predict kind of how the different dimensions are linked together and how the structure might behave under different circumstances. So particularly for modeling, it gives you a very easy way to describe very, very complicated materials. This is also then used in video games, where if you want to sort of have a very realistic world, you don't want to have to save every piece of detail about the world. You want to kind of save information about how it scales so that it looks realistic. And then you can just save very coarse information on your system and have a nice rule that generates the much higher resolution information when you need it. And then you can have a very small video game that has a huge amount of detail. And if you're not able to find these sort of scaling laws or these properties, then you can't kind of compress information nearly as well, which is very important. The final technique, and this would be then more, or the final technique I'll mention here, of course there's hundreds of other ones, is the two-point correlation function, or there's a number of different ways to characterize or to call the same thing. But basically this is used very heavily in material science for modeling. And so this is looking at structures, and rather than focusing on how the structure itself looks, you try to come up with a function to describe that structure statistically. And so here what you do is you sort of take a point in your image and you calculate what's the probability that a surrounding point is also part of your structure. And so it gives you a function that then shows how your object is distributed in space without having to sort of come up with a skeleton or segment different regions out of it. You can just feed it an image and it comes out with these probabilities. And where it's particularly useful is when you're dealing with sort of random or quasi-random systems, that it allows you to describe them very well and see the structures that they have, even if there's a lot of variation that's going on between them. And so one of the places we've used these tools is when you're looking at sort of like clays or compressed clays, that you want to figure out where the layers are inside the structure. And the layers usually aren't very clean-cut sheets. The layers are usually sort of random, thin, thick regions that are slightly larger in one dimension than the other one. And if you use a two-point correlation function, this comes out quite clearly. And if you try to sort of do component labeling and find objects and look at oplateness or anisotropy, it's very difficult to assess where the layers actually form. And so it can be very robust. It's also very commonly used in other simulations and analyses, because once you've come up with this two-point correlation function, you can sort of build up other analyses on top of it to see how the mechanical properties of this material would be. And so there's actually a very interesting group at Princeton that spends a lot of time developing these tools further. So that's it, unless there's any questions. So the exercises for today are in KNIME again. There's simple versions of it, which I'll try to update in IPython. Are people doing the IPython exercises? Or trying to follow them up in IPython at all? Okay. I mean, if you have questions, both Johannes and I can answer them because we know how those tools work. But yeah, I'll try to update the workbook so that they have more of the functions that you need, because a lot of them aren't always easy to find. Or, as you see with IPython, that you need 5 different packages to do it correctly. And so this is the exercise 6 that we have here. And this kind of shows you how you calculate the different distance maps, how you change the distance metric that you use inside it, and how you do things like watershed. And so this gives us, for the watershed here, you have to combine a couple of different functions in order to get it out, but it gives you the same result as you would get with other tools.